All right, so now we're in the last chapter that we cover in this class, chapter 16. Chapter 16 is essentially the basics of vector calculus. Depending on your perspective, we haven't really been doing any vector calculus. We've done a lot of work with vectors, and we've done a lot of calculus, but the calculus has been on what we've been calling up until this point multivariable functions. We're going to give a new name to those types of functions in this section as well. This section is going to focus on, this chapter is going to focus on what we call vector calculus, and we're going to be looking at a lot of different types of integrals throughout this chapter, line integrals, surface integrals, volume integrals. We haven't dealt with these before, but they are very intimately connected to types of integrals that we have seen. And so a big part of this chapter is providing links between the work that we do with vector calculus and the work that we've already done in multivariable calculus. 16.1, we're not really looking at much in the way of calculus, though. We're going to be defining vector fields, which is kind of the environment that a lot of our work in chapter 16 is done in. So let's start with some definitions. We're going to say let's let D be a set in R2. So we've been calling these plane regions up until this point. We define a vector field on R2 to be a function that assigns a two-dimensional vector to every point in D. So basically, a vector field on R2 takes as its inputs vectors in R2, and its outputs are also vectors in R2. In class, I gave a notation for this. So the function f that's being described here is mapping R2 or a subset of R2 into R2. This definition down here is very similar, where we have a function mapping R3 into R3. If I wanted to be a little bit more accurate, I would have made this D and this E, where D and E are the subsets of R2 and R3 respectively that are described here. But this is more to kind of paint a picture of what the domain and range of these functions look like. So again, vector fields take vectors and map them to other vectors. Where this differs from what we did in chapter 15 and chapter 14, where we're looking at multivariable functions, is those functions would take a vector either in R2 or R3, or in the more general case, Rn, and the output would be a scalar, not a vector. For that reason, those multivariable functions that we've been working with up until this point, we're going to start referring to those as scalar fields. And the scalar there refers to the output of those functions, whereas here the output is a vector field. So now again, in the context of what we've been doing, if you have a two-variable function, f of xy equals z, for example, graphing a function like that requires three dimensions. You have the output, which is one of the variables, and the input, which makes up the other two variables. And we saw that graphs of those functions look like surfaces. But what does the graph of a vector field look like? Well, we approach it in kind of a different way. So if we want to graph, for example, a vector field on a plane region R2, then this is one example of what that might look like. So again, the inputs are points in the plane. The outputs are vectors that are associated with each one of those points. And so what we're doing is we're placing a vector whose initial point occurs wherever the input point would have been in the plane. And what that does is that fills up the plane with vectors associated with each of those input points. If you've had differential equations before, this might look really familiar. You may have encountered this elsewhere also, in something called a slope field. That's a different thing. It looks very similar to a slope field, but this is not the same thing. So if you're looking at this and thinking, oh, I've already done this in differential equations, you haven't. If the vector field is taking points in R3 and mapping them to vectors in R3, then the vector field is going to look similar to this, but in 3 space instead of 2 space. So to each point in R3 that belongs to the domain of our function, we're attaching the output vector to that point by its initial point. So let's look at an example where we're given a vector field and we need to graph it. Now, a lot of the examples I do in this section are straight out of the book. So you can refer to that as well. I'm using those examples because, one, they're good examples and they have there's some interesting interpretations of those, but also I can use the graphics a little bit more readily. I struggle with drawing these and making them look good. So here's an example of a vector field, what it looks like algebraically. F of xy equals negative yi plus xj. Notice the input is a point in R2, xy. And the output is a vector in R2, negative yi plus xj. So in order to sketch this vector field, you can't sketch the entire thing because the plane consists of an infinite number of points, which means there would be an infinite number of vectors to draw. Even in a confined region like this, there's still infinitely many points in here. So we're only picking sample points and plotting those vectors. But if you look here, we started by making a table. So we pick points. Here we used the point 1, 0, plugged it into the function. That would give me the point, the vectors 0, 1, or 0i, 1j, which is what we're seeing right here, just in component form. And we do that with several other points. 2, 2, for example, gets mapped to the vector negative 2, 2, and so on and so forth. Now if you go over here, we look at where we graph these things. So the point 1, 0 would be here on the x-axis, and the vector that we got from plotting that point was the vector 0, 1. Well, that has a 0 for its x component and a 1 for its y component. So that means it would be pointing straight up in parallel to the y-axis and have a length of 1. That's what you're seeing right here. But notice the initial point of that vector is placed right on top of the input point that we use to come up with that vector. And we do the same thing for all of these. The point 3, 0, for example, which is up here, it once plugged into this function produces the vector 0, 3. So that's going to be this vector here. So you can kind of see, I think that's actually a typo. No, never mind. So this is the idea behind how we deal with vector fields, what their graphs look like. And there's lots of different interpretations that we can attach to these depending on the context. So for example, a vector field could represent air currents, for example. If this two-dimensional plane here represents sort of an eagle-eye view of a large region or, a country or something like that, and we're looking at air currents going in different directions at different magnitudes and things like that. It's you can kind of see how there's some interpretations that your book has some graphics that that indicate that kind of a thing. A lot of what we're looking at when we're talking about vector fields are forces. So probably either at the end of this video or in the next video, we're going to define force fields, where they're vector fields that represent a force acting on individual points either in the plane or in 3 space. But I want to work with this example a little bit more. So here's what the diagram or the graph of this vector field looks like. And now let's investigate this a little bit more. So it says in the example above, show that every vector in the vector field is tangent to a circle centered at the origin, and that the magnitude of each vector is equal to the radius of the circle it's tangent to. So you can kind of see the way that this was drawn. These 4 vectors right here definitely seem to be tangent to a circle. They even drew a circle in there. And then these other vectors out here, you can kind of see that they appear to be tangent to a circle centered at the origin. But how then do we actually prove that? Well, if I take just some arbitrary vector here, and let's just say that this point is the point xy, then its position vector would have components x and y, right? So I'm talking about the position vector for that point. Now the vector in the vector field that this point is mapped to, we know would have components negative y, x. Negative y, x. Now one way that we could tell that a vector is that this vector is tangent to a circle centered at the origin whose radius is given by this vector right here is we use a property that we know to be true. If I were to take this vector right here and sweep it out in a circle, then any vector that's tangent to that circle would be perpendicular to this vector. That's a property that we've looked at in our class. It shows up in geometry. Tangent lines to circles are perpendicular to the radii of that circle, or a radius of that circle. So I want to verify that this vector is orthogonal or perpendicular to this one, but we have a method for checking that. We use the dot product. So if I were to take my position vector xy and dot it with the vector from the vector field, negative yx, this is equal to negative xy plus xy, which is equal to 0. Okay. Now I chose an arbitrary vector for that, so that would be true of any vector in this vector field, which means all of those vectors would be tangent to a circle centered at the origin, and the radius of that circle would be given by this vector right here. It says the magnitude of each vector is equal to the radius of the circle it's tangent to. So that's the next part of this. What we're saying is that if this point right here, this vector right here is the vector that's tangent to this circle, then its length would be the same as the radius of the circle. But again, this vector right here, xy, is being used to represent the radius of that circle. So basically I'm saying that these two vectors have the same magnitude. And that's easy to verify. The magnitude of xy is equal to the square root of x squared plus y squared. The magnitude of that vector from our vector field, oops, I just realized I've been writing down here and you can't see what I'm writing. The magnitude of the vector in our vector field, negative yx, would look like this. Square root of negative y squared plus x squared. But of course that's the same thing as the square root of x squared plus y squared. So these two things are equal. And that's establishing the second part of this. Okay. We have a number of ways of interpreting what a vector field is in context. So we're going to look at a few of those. One type of vector field is something that we call a velocity field. So a velocity field is, oftentimes we're going to see this in R3, where we imagine a fluid in R3 passing through, or a fluid that's moving around, and the velocity field, the vector field that we're seeing here, if you can see these arrows that are sort of representing the vectors in this field, they represent the velocity of individual particles at different points. So we would call that a velocity field. We're going to look at that throughout this chapter, and a lot of the time we're thinking of these things as fluids. But a little bit more interesting in the context of physics is what we call force fields, of which there are many types. And the one that we're going to look at down here is called a gravitational force field, or just a gravitational field. And I think actually I'm going to save this for the next video because we're starting to run out of time on this one.